So far what we've done is we started off in the sort of real but messy world of analog electronics, where electrons flow and time runs continuously, and voltages can be any value. And we tamed that beast by imposing a digital discipline where we came up with a representation for bits, for zeros and ones, and used that voltage representation. And we used that along with some voltage-controlled switches to design machinery that is able to signal digitally and to process digital signals using Boolean logic in order to perform interesting functions. And the rest of this course is really thinking about interesting functions we can build with logic, and in particular we'll be spending a lot of time building ourselves a computer. Or you'll be spending time building a computer, and we'll be talking about how to do that. And so the first step in that stage was to design combinational logic, and we came up with the static discipline and truth tables and various implementation strategies to actually build logic gates. And it's interesting to ask oneself, is that all we need? Can we actually build a computer with what we know so far? And the answer is no, we're missing one thing. So what's the thing we can't yet do? And so here's a little word description, but it's easier to watch the animation. So when our assistant here presses the button, the light goes on. And if he presses the button again, the light goes off. And on and off. And what's interesting about that is that the light, the state of the light, which is the output of this particular device, is clearly independent of the state of the button. In other words, it's not on when the button is pressed and off when the button is not pressed. That you could implement in combinational logic. The behavior that's shown here, which depends on the history of the button presses, in other words, the light basically changes its state from on to off every time the button is pressed. This notion of history, where the function of the output, in this case the state of the light, is not simply a function of the state of the input, which is the button. It has to do with what's happened in the past. So we're going to have to change or add something to our toolbox that lets us talk about the notion of state. And state is sort of a summary of previous history, sort of encapsulated, we've extracted from that history the information we need and remembered it. So the notion of a state is sort of our way of capturing the notion of a memory. And so we have a notion of state. And the other thing that we sort of notice is that there's this notion of pushing the button. So we're talking sort of about button pushes. The notion of events as opposed to just, is the button pushed or not. There's sort of like the same thing, the difference between a mouse click and sort of just where we're sort of trying to identify an instant in time. And you'll see that show up in today's lecture too. So we're going to add to we love to use clouds here as a representation of combinational logic. And combinational logic, of course, has some number of inputs. And we know that if the inputs to the combinational logic cloud, our logic circuit, have been stable for at least TPD, we can expect to find digital stable values on the outputs, and they will not change any further until we change the inputs again. We're going to add to this basic recipe, this basic idea of how to manipulate digital information, a new device called a memory device. And the notion is that it represents the current state, encoded in some number of bits. Now, this sort of very high level, notional diagram of a digital circuit is actually complete now. With a notion of state and a state holding device combined with combinational logic, that, if you will, is the schematic diagram of every digital system we can build. Your laptops have a lot of state in them, millions of bits of state. But conceptually, they have something that holds the state and something that manipulates the state, combines the current state, combines it with the inputs, produces new outputs, and a notion of a new state. And then at a certain instant of time, we can choose to move to a new state. And then the whole process repeats again and again. We're going through a sequence of states. So this type of logic, the combination of memory devices and combinational logic, is called sequential logic. So called sequential because we're going to go through a sequence of states. And the notion is, when do we actually change the state of the device? Well, it depends on what we're trying to do. you have a clock. It's a periodic signal that goes high every billionth of a second, or half a billionth of a second, depending on if you have a 1 gigahertz or a 2 gigahertz processor. And so your computer is busy updating its state with a new state, a billion times a second. And that's what makes the world go around, at least in terms of digital processing. So we've introduced some new notions here. We have a notion of sort of a current state, which represents our notion of history up to now. We're going to combine that with the inputs to compute a next state, and then at a certain instance of time, we'll transition to the next state and repeat that recipe again and again and again. So we're going to spend a little bit of time now thinking about how to actually build this storage device. Yes?
Doesn't it cause issues because in general we're not allowed to have cycles?
We're not allowed to have cycles.
That looks suspiciously like
This looks suspiciously like a cycle, and in fact, this will be the only cycle we allow ourselves. In some ways, the only place that we're going to allow ourselves to sort of make this loop is right at the storage elements. And you'll discover in a moment that we actually, the actual circuitry that we're going to use to build a memory device is itself not a combinational circuit. It will be a circuit that itself has a positive feedback loop in it. That's how the storage will be implemented stably. So it's a good observation that, in fact, we're breaking our notion of allowing ourselves a cycle, but they're going to be engineered cycle. You can't willy-nilly make a cycle. You can only make a cycle, in a sense, at the input and output of a storage device. Okay, so cycles that don't include one of these storage devices will continue to be disallowed. We won't allow combinational cycles.